Welcome to the Podkey summary of Explore Distributed Inference and Training with MLX from WWDC 2026. Apple quietly put together something pretty interesting here. A way for multiple Macs to behave much more like a real high-speed compute cluster, using Thunderbolt 5 as the link. The big picture is RDMA over Thunderbolt, JACCL on top of that, and MLX to make it usable for actual inference and fine-tuning. And the practical hook is hard to miss. This can push model work across several Apple Silicon machines, including models too large for one box, while keeping everything local and private. Starting in macOS 26.2, Macs get support for RDMA over Thunderbolt 5. RDMA stands for Remote Direct Memory Access, and the useful plain English version is that one Mac can move data straight into another Mac's memory with very little CPU overhead. That matters because distributed inference and training live or die on fast, low-latency communication. If the machines spend all their time waiting on each other, the whole cluster feels fake. RDMA solves the raw transport piece, but only that piece. It moves bytes around very efficiently. It does not by itself tell your software how to do things like synchronizing model updates or sharing tensors. That's where JACCL comes in. Apple open-sourced it as the collective communication layer that sits on top of RDMA. So instead of every developer hand-rolling networking logic, JACCL exposes the operations people actually need, like all reduce and broadcast. If you've done any distributed machine learning, those are the verbs that matter. They're how nodes combine gradients, share activations, and stay in sync. And because JACCL abstracts the transport layer, this is not limited to machine learning. In principle, any distributed workload that needs fast collective communication can use it. One of the nicer details here is how JACCL handles topology. A full mesh means every node talks directly to every other node. That gives the lowest latency for small messages, which is great when speed of coordination matters more than bulk transfer. A ring uses fewer cables and can make better use of available bandwidth by grouping Thunderbolt ports toward neighboring machines. So instead of making users pick one layout and hope for the best, JACCL automatically chooses mesh for latency-bound operations and ring for bandwidth-bound ones. That's the kind of engineering choice that saves people from a weekend of benchmarking and cable rearranging. On the model side, there are two different ideas to keep straight: tensor parallelism and pipeline parallelism. Tensor parallelism splits each layer across multiple nodes, so all the machines work on the same token at the same time. That can speed up inference in a very real way, especially for large models, but the trade-off is constant communication between nodes at every layer. Pipeline parallelism chops the model by depth instead. One machine handles one block of layers, the next machine handles the next block, and so on. That cuts down on communication volume, but it does not make a single token move faster, because the token still has to pass through the pipeline step by step. The demo numbers are solid enough to make this feel concrete. Running the 27 billion parameter Qwen 3.6 model across 4 M3 Ultra Macs produced tokens at nearly 3 times the rate of a single M3 Ultra. It's not a magical 4 times boost, and that's normal. The exact gain depends on the model size and architecture, plus the communication overhead you're paying. Still, nearly 3x on 4 machines is a strong proof that sharding across the cluster can convert a one-device workload into something meaningfully higher throughput. The more eye-catching example is a trillion parameter model running locally. Kimi 2.6 needs about 1 terabyte just for the weights, even with 8-bit quantization, which is more than a single M3 Ultra can hold. Spread that across 4 machines with tensor parallelism though, and suddenly it fits. Using MLX.launch with a generated host file, the whole thing can run on premises instead of getting kicked out to the cloud. That's a big part of the appeal here. If your concern is privacy, compliance, or simply not wanting your build to develop a personality, local matters. This setup is not just for inference. For fine-tuning the 9 billion parameter Qwen 3.5 model, a single M3 Ultra processed about 180 tokens per second, while a 4-node cluster reached around 600 tokens per second. That's better than a 3x improvement, which lines up with what you want to see from data parallelism. In data parallel training, each node keeps its own copy of the model, works on different batches, and then averages gradients with the others. It's a very familiar scaling pattern in distributed training, and the fact that it works this cleanly on a small Apple Silicon cluster is the notable part. Apple also seems to understand that none of this matters if cluster setup is miserable. The MLX.launch command handles SSH startup across nodes using a JSON host file that includes host names, local IPs for JACCL coordination, and the RDMA device names for Thunderbolt peers. There's also MLX.distributed_config, which can auto-discover the topology, disable the Thunderbolt bridge, enable RDMA, and bake in environment variables like MLX_metal_fast_synch_1. If you want to go lower level, MLX exposes distributed primitives in Python, Swift, and C++, so developers can manually shard layers, call all reduce directly, or even embed models into macOS apps. And JACCL itself can be built without MLX, which means its C++ communication layer can support distributed applications beyond AI. The real takeaway is that Apple now has a surprisingly coherent stack for private local AI clusters. RDMA gives the fast link, JACCL gives the coordination layer, and MLX gives people a practical way to run and train models across multiple Macs. So the pitch here is not that a desktop setup replaces every cloud deployment. It's that cloud-like scale and speed are getting a lot closer to something you can put on a desk and keep entirely under your own control. It's a pretty striking shift when Thunderbolt starts sounding less like a peripheral port and more like cluster fabric. And if local AI was starting to feel cramped by single machine limits, this is a meaningful way out without leaving the building. This episode was generated by Podkey. Create your own at podkey.fm.